I would like to credit Tobias Kuhn from electrondust.com for inspiring this project. He also created a 4-servo robot arm with an electromagnet end effector on a Raspberry Pi using a 74 LS241 octal buffer. Instead of using OpenCV, however, he ended up using a library that was written by Jesse Merritt back in 2015 that does things like edge detection manually, manipulating and comparing pixels, for example, which, given OpenCV's power, is not really necessary anymore. Furthermore, he unfortunately didn't document his project to the level that I needed to replicate it, so I kind of had to reverse engineer it. I would also like to thank Adrian Rosebrock at PiImageSearch.com for his amazing OpenCV code. I just slightly modified his code to meet my needs. The cool thing about this project is that I'm able to convert vision data into robotic movement. I haven't seen many DIY robot arm videos that implement vision on YouTube. You'll want to also familiarize yourself with his code because Adrian documents it very well. And I would recommend that you play around in Photoshop or GIMP with a basic 400 by 400 pixel solid color image. It's good to understand the basics of how to manipulate an image the old school way before using OpenCV. These libraries are pretty much used on every Raspberry Pi project. In the Vision libraries, you are importing OpenCV represented by CV2. NumPy almost always accompanies OpenCV because it's a library that adds support for large multi-dimensional arrays and matrices. PiCamera allows you to take snapshots and modify them in many ways. IMUtils is a great library created by Adrian Rosebrock at PiImageSearch.com. By the way, don't forget that the servos are numbered as follows. The shoulder servo, the one closest to the table, is ID 4. The elbow servo above the shoulder is ID 1. Wrist is ID 2 and hand is ID 3. A lot of people might get confused and think that the shoulder servo is actually ID 0, but it's not, it's ID 4. In front of us, we just have some constants whose purpose will become clear as we move down the file. A lot of this was copied from Jesse Merritt's Dynamixel library used by Tobias at ElectronDust. If you don't know what an instruction packet is, you may want to view my 5-part video series on YouTube before you continue. Here you notice that we have a write instruction 03, and that's just a register based hex number. Goal position, same thing. These are all obtained from the control table. And if you look at the video series before, it'll go into great detail about that. The relay is using GPIO 17, channel is using GPIO 18. These are just pretty standard. These are outgoing communications, so you would want to specify these. And then as far as the serial, this will either be TTY-S0 or SER0. These two just control the 5-volt relay. when it's on and off. Sometimes you terminate the program before the relay has had a chance to turn off, so it's still on. So when the program is running, it'll turn off the relay just to make sure that it's off when the program starts. This is the computer vision section. As you can see here, I link the exact page from where I got the code. So here you're creating an array, a 4x2 array with this command. And then it's pretty neat how somebody figured out that when you take the minimum and the maximum, you're going to get the top left corner, the bounding box top left corner, and the bottom right corner, which is the farthest point. Here you're actually taking the photo, you're using your PyCamera library. You're specifying the resolution, which is, it doesn't have to be very sharp, it just needs to be able to detect that an object is there. And the reason we're doing a zoom is because the platform that the arm is sitting on is not wide enough, so there's a little bit of contrast along the lines, and that throws off how the image is being processed. Here you take the photo and you're actually giving it a name and writing it to the hard drive or the SD card. You convert the image to grayscale so it'll be easier to manipulate on one channel only. If it's color, it's 3 channels. If it's grayscale, it's just 1 channel. We're using the canny edge detection, and you have some thresholds here. So it says basically anything under 25 becomes black, anything over 100 becomes a white pixel. Dilation is just a way to expand the existing pixels so that it's like, for example, the lines are broader. And then here is where you start building the bounding box. This can conceivably run numerous times depending on how many objects are found on the platform or / table. We define a global variable here that will be used to calculate the area, and then based on the size, on the bounding box size, it'll determine whether it's a small object or a large object. And then for the rest of the code, it just begins to figure out where the bounding box should be, and it calls the function that I showed you at the very beginning that figures out the 4 corners where they should be. It'll wait 3 seconds and then it'll destroy all the windows so that the program can continue. That's when you see the actual image on the screen disappear. And then here we have our instruction packets. I needed to put the arm in neutral position because when the arm rotates from one end to the other, if you don't have it in neutral position, meaning balanced, it starts to wobble a lot. This information is pretty self-explanatory as far as what it does. So these are the instruction packets that I was telling you about, and you'll want to watch the previous videos in the 5-part series because it goes into great depth about what these are and what they're used for. And then it just, it tells it where it wants servo 1 to go, servo 2, servo 3, and now we come up to the arm photo. So this will position the arm to take a photograph. This is when it's positioned right above the object to take a photograph. Most of the time it'll go to arm neutral just so they can start fresh before it makes the movement. This part about the bitwise operators is pretty complicated if you don't know anything about bitwise operators, but I try to explain it here, and if you play around with it, it should become fairly familiar. There are some bitwise calculators online that I'll link to, and you can play around with those. They're pretty neat. So here you can just change this number here, the 650, and you don't have to do anything else, because you have to calculate a checksum, and the checksum is going to be calculated by these bitwise calculations. Same thing with moving speed. If you want it to go faster, all you need to do is change this number here. So the information that I have highlighted here is mainly it computes the checksum automatically based on all this code here. And this is, I included this because a lot of libraries, especially some of the older libraries, use this ugly code to calculate the checksum, and so I've included it here just for your information. But for the most part, on the rest of the code, I just calculate the checksum manually using the checksum calculators online. And so we're still trying to position the arm so I can take a photograph of the object. So you want to move servo 1, servo 3. The arm pickup is going to position the arm so that it can pick up the object with the electromagnet. Again, we're going back to our arm neutral position just to make sure it's balanced before it starts rotating on servo 4. And this is the stuff that you observed on the video at the very beginning of this series. Finger move down to the table. This is when it does its sweep. As you can see, this is where the relay turns on right as it's about to do a sweep. Goes back to neutral position so that it can rotate towards the little ball. This is the code that's used right before the object is dropped into the bowl. Wrist perpendicular to elbow. Finger move up closer to the candy dish. Elbow 90 degrees straight up. And then the relay is turned off to release the object. This will move the shoulder to the large bowl, and this will move it to the small bowl. And then we have a for loop. So in general, when I presented 3 objects, which were the binder clips, the lid, and the screw, those were just 3 of them, right? So you can make this number as many as you want. I mean, I've made it 20, and I have had 20 objects being picked up and dropped just for testing. And this basically controls the process. Move the arm to a position, and get it ready to take a photo. Actually take a photo, pick up the object, determine whether it's larger or smaller than 10,000 pixels, print on the screen what it is, and then you close the serial connection and you clean up the GPIO pins.